Hello and welcome to 12-lead EKG Interpretation 2019. My name is Leif Tobler, and let's get rolling. No disclosures to make. I'm just making this video to help get you guys better at reading rhythms and EKGs, particularly 12 leads. No conflicts of interest. First focus is going to be on anatomy, physiology, electrical flow through the heart. These things are really important for understanding later on how damage to the heart can affect all of these other systems. First and foremost, your heart is approximately the size of your fist in most scenarios. The heart lies obliquely in the chest. It doesn't actually sit vertically like most people think. So if you look at the way this picture is set, your heart isn't this, the way that most folks draw it. It actually is more of a off to the side in your chest. There's multiple parts about that picture that aren't anatomically correct, but the idea is it's tipped to its side, where you have the apex down here, and this is considered the base. The heart is essentially an upside down triangle where your ventricles are down here and your atria are on this end. People in the 1600s made this stuff up, not me. That's all I can offer you. Last important thing to keep in mind about the heart is that it's surrounded by a thick sheath known as the pericardium. Really, really tough, fibrous, doesn't have a lot of give. That's why when you fill the pericardium with blood or other fluids, you can wind up with cardiac tamponade. Anyhow, layers of the heart. You have the outermost portion of the heart, the epicardium. It's just like your skin, epidermis. Next layer down is going to be your myocardium. Myo is muscle. And your third innermost layer is going to be your endocardium. Important things I want you to pull out of all of this. The heart is inside out compared to the rest of your body. If you think about your arm, for example, your arteries, your veins, your nerves, those are all internal, running through the deeper portions and then feather out and spread to your skin and your fingertips and all of that. The heart's actually backwards, where the coronary arteries, the nerves, and even the lymphatics are on the outside of the heart, feeding into it. Almost kind of like, well, for lack of a better phrase, tree roots. If you think about it, you've got your main tree, and then it branches down, and then that branches deeper, and etc. through. And that's how the heart gets fed, from the outside in. Your myocardium is responsible for the contraction. It's the meat of the heart, the muscle. That's what does all the work. The endocardium is even cooler yet because it is made of mostly connective tissue. Cartilage is actually what the innermost part of your heart is lined with. Important things. Cartilage doesn't really conduct electricity all that much. It's also super slippery, and it is one continuous lining between your arteries, veins, and your heart, which is super cool because think about it, that blood has to flow through. You want to make sure that it doesn't get hung up on anything along the way. Important things that come with all of this. Your electrical impulses are designed in a way that they actually start, if you think about the wall, well, we'll come back to that, but we'll talk about the way electricity flows through the heart itself and influences the way it contracts. And this layout of the blood feeding into the heart from the outside plays an important role. Chambers of the heart. Simply put, you have your right atrium, right ventricle. You have your, I'm going to go ahead and mark this, pulmonary artery, which then goes to the lung. You then have this here, which is your pulmonary vein, which is bringing blood back from the lung, actually. And then the pulmonary vein feeds into the left atrium, and that then goes to your left ventricle. So what's the path of blood flow from the body? Well, it will come either this direction through the superior vena cava, or it will come from the bottom half, which is your inferior vena cava. Both of those will feed here into the right atrium. That blood then flows into the left ventricle, which then flows up through the pulmonary arteries and out through the lung, gets oxygenated, comes back through the pulmonary vein, into the left atrium, left ventricle. Left ventricle contracts and it spits it up out through here into the aorta and the rest of your body. That's the important things about the blood flow. How does the body manage to do that? Well, electrical impulses create a two-piece contraction. The first piece is going to be your atria. Your left and right side will be the first to contract. I'm going to go ahead and switch colors here to green. Your sinus node is responsible for triggering a normal impulse. That will then cascade through the heart, following along some pathways, but will ultimately cause the atria to contract first. That's going to shove the blood through both atria, simultaneously compress them down flat, thus helping give that atrial kick to the left and right ventricle. When the left and right ventricles contract, it's influenced by the following sequence. So sinus node triggers, electricity flows through. Electrical travels faster than mechanical. So that electricity, after it has flowed through the atria, once it's finished flowing, that's when contraction actually starts. The AV node does receive the signal that a contraction is being stimulated, but it doesn't relay the signal immediately. It actually sits on it for a brief period. And that's why after your P wave, you get a little bit of a break here. And that's the AV node doing its job. That AV node sits for a second, allows the mechanical to catch up with the electrical. It has an internal timing circuit built in that it will then release at the appropriate time. When it releases its signal, it'll actually travel here through the bundle of His and then down through the right and left bundle branches, appropriately named for each side. Bundle, what's it a bundle of? Well, it's actually a bundle of Purkinje fibers. Kind of think like fiber optics or a telephone cord. So that electrical signal will actually travel down the entirety of the septum first, all the while radiating out beyond those points. Electrical travels faster than mechanical. So the center of the heart, the septum that divides the ventricles, will be the first thing to contract. Super clever design. The next thing to contract is going to be down here, the apex, and followed by the outer portions of each ventricle. Those will be the last to contract. And this is really, really clever. You have the septum contracting first. That creates a nice rigid wall so that then the left and right ventricle, when they perform their contractions starting at the bottom, it's almost like folding a book up, that you go from here to here, and as you swing it shut, it's going to help expel all of the blood out. So think how this blood has flowed in through here. Blood is just sitting in the ventricle. So if this contracts first and then the apex and the side, as that contracts, that's going to help expel blood down and out much more efficiently. And it happens on both sides. Clever, clever design. Coronary arteries. So let's talk about how the blood gets fed to the heart. The heart is a powerful, powerful muscle. Think about it. It's about the only one that never gets to take a break. All of your other ones usually get a slack a little bit, you know. You have a right and a left coronary artery. Those coronary arteries are fed directly off of the aorta. And you can kind of imagine this one flowing underneath this. This is the pulmonary artery, by the way. You can imagine that that left one is probably right here. And you've got your right one. So we'll talk about a few different things. First off, when does the heart get its blood flow? Well, if you think about it, your brain, your kidneys, the rest of your body receives blood flow during systole. Well, if the heart is contracting during systole, I don't know about you, but when I'm trying to lift something and I have those muscles flexed, they'll tire out. Well, that's because when a muscle is contracted, no new blood flow can really get into it. You have to relax the muscle. So to that end, the heart will contract systole. That puts blood out to the rest of the body. When the heart relaxes, diastole. When the heart is relaxed, that's when it gets its blood flow. And this is really cool. So that, well, I shouldn't actually say cool, but point out that when the heart is beating fast, there's not as much time for relaxation, and so it will not be receiving as much blood flow as it would when it is beating at a slower rate. Slower rate means more relaxation, more time in between beats, therefore better chance to receive the blood flow it needs. So that's an important thing. How does it accomplish this? This is a really great design. During contraction and blood is flowing out, your valves are open. So heart contracts, valves open up. When they flip open to the sides of the aorta, they actually block the coronary arteries. Then, when the heart relaxes, diastole, these valves will close, and when they close, that opens things up so that blood can flow into the coronary arteries. So heart contracts, blood to the body. Heart relaxes, valves fall down, blood flows through there. It's one of the reasons why we get a little excited about diastolic hypertension, because if you have diastolic hypertension, that's the pressure that's being forced into your coronary arteries and can cause a lot of damage if it gets out of hand. So that's part one, when it gets the blood. Well, how does it flow? Well, that blood will flow from these larger arteries and then will branch down. And this is why I use that example of tree roots from earlier, in that it starts at one major feed point and then becomes progressively smaller, feeding into the heart itself. From a real close perspective, if you want to think about the wall of the heart, I'll just kind of make a cross section out of this, and we'll make these little loop-de-loos for blood. And we'll say this is the inside, outside. Blood will flow. I'm just going to make a nice contrast here. We'll use orange. Blood flows in. And if you think about the way this is designed, is you have a large artery here, which then breaks off into two or maybe three smaller ones, which then breaks into a smaller one yet. So not only do you have this pattern on the outside of the heart, but even internal to the heart as well, do you see this branching. And that's important because when the heart contracts, it contracts from the inside to the outside. And so as it contracts this direction, because the electrical signal flows along the inside of the heart first, you will see these compress sequentially this direction. And then when the heart relaxes, it relaxes the opposite direction. So then blood will be able to flow the direction it should. Also really fun because it compresses in this direction. Every heartbeat kicks out all of the venous blood as well, because you've got all these veins that will then come together to make a larger coronary sinus, because wherever red blood goes in, blue blood needs to come back out. That's just a rough overview of that portion. But coronary artery circulation. Zones is probably the bigger part of what we need to discuss now, and it's this. So the right coronary artery will feed that right half of the heart. You can probably imagine that the sinus is somewhere in this zone, and that you've got your ventricles somewhere around here. As the right coronary artery feeds and down through here, you'll see a couple different things. The right coronary artery feeds the inferior portion of the heart in pretty much everyone. The left coronary artery has two portions. It has an anterior descending and a circumflex. The circumflex is for the lateral portions of the heart and posterior, whereas the anterior descending does one job, and the anterior handles this. Now, is there some overlap? Absolutely. And circumflex is here. To continue looking at things, if you look at the back side of the heart, you'll see that this is the circumflex, and that's feeding that lateral and posterior. The right coronary artery not only feeds the inferior portion of the heart, but it also does some of the posterior as well. And that would be this section is here. Inferior and posterior. There is such a thing as left and right-handedness of a heart, and that has a lot to do with this section in the back. Sometimes this will reach all the way over and connect to this artery, and your circumflex stops early. About the only way to find that out is when you get your first heart cath. So don't focus on that too much, but do realize that there is a left and a right-handed heart that exists. The other reason that we're really focusing on this right now is that I wanted to illustrate that specific coronary arteries and sections thereof feed specific portions of the heart as well. So you could imagine that if a person winds up with a blood clot right here, since that pointer's right there, that is going to block all of the blood flow below that point, and so can very likely cause an MI in this entire section of the heart, as well as everything that's connected beyond that. And so by having a large blockage in your right coronary artery, you have just knocked out almost entirely the right ventricle and posterior right ventricle, as well as part of the intraventricular septum, the IVS. And so let's talk about that a little bit. Vice versa, if you think about blockages in your LDA, So this is the LAD. And over here is your LCX. Think about that if you have a blockage here, you're taking out the anterior portion of your heart, whereas if you have a blockage in your circumflex, you won't see much here, but a blockage in your circumflex can take out a large portion of your left ventricle. So here's some basic information to talk about those in detail. The numbers on these aren't drastically important, but we will continue referencing them as we go forward. So your RCA feeds just over half of the sinus nodes out there in the world, whereas it feeds essentially the entirety of your right ventricle, and the right coronary artery feeds 90% of AV nodes. So it would make sense that if you have an AV node block, so your first degree AVB, or second degree type 2s, probably is due to an RCA occlusion. I know I didn't spell it right, but you get the picture. This latter part here talks about the posterior descending artery on that back side of the heart, and how you can have a left or a right-handed based on whether it's the circumflex or the RCA that feeds it. Most importantly, this posterior descending artery feeds the inferior 1/3 of the IV septum and the posterior wall of the left ventricle. Most cases, it is the right coronary artery that takes that. Left coronary artery, so the LAD and the left circumflex, LCX, supply basically everything that's not taken care of by the right coronary artery. LAD, 2/3 of the now the anterior 2/3 of the IV septum, because we just talked about how the posterior third, posterior wall of the IV septum. Also, your LCX is going to feed those other sinus nodes, the rest of the AV nodes, part of the inferior posterior left ventricle. And then there's the obtuse marginal, is really important for that lateral left ventricle. For today, we're really just going to focus on LAD, LCX, and the right coronary artery. Electrical conduction. We'll just kind of talk about this and wrap things up here shortly. Electrical conduction is super cool. We've touched on this a fair amount, so we'll not dwell on it. But your sinus node is where your normal electrical signals occur, fires at 60 to 100 beats per minute. It is carried through intranodal pathways, and that does speed up the signal a little bit, kind of the difference between texting someone versus sending them a mail through the letter. You've got your AV node here, which again will hold on to that information for a split second, hold on to that electricity, and then relay it on down through the bundle of His, where it divides up into the left and right bundle branches. And of course your left bundle branch has a posterior fascicle and a anterior fascicle as well. I do want to talk about the way electricity is conducted through the heart. An important portion of that is actually the musculature itself. And so I'm going to draw some muscle here real quick. The cardiac cells are really, really unique. In fact, that they're intercalated, however you'd like to pronounce it, that you've got divisions in them. Each cell is essentially sewn to the next one, but they branch off so that this cell feeds the next cell, which branches out and feeds the next cell, which is part of a branch that feeds another cell, that then feeds another cell, etc. And so what this does is it creates a scenario where if you fire off or create an electrical impulse in a single cell, let's say that this one was the first to fire, that electricity is going to be manually conducted to this cell and then to this cell. Well, this one's also firing it this direction, and this one goes to this one, so that this cell here would actually receive information from one or both of those. And of course it's going out this direction, and that's why you get that ripples in a pond effect, that it travels in all directions over time. And so that's why when the sinus node fires, you do get that effect, but that's slow. It's like handing a letter person to person to person. It takes a lot of time, which is why these internodal pathways exist, to try and get that information across faster. That's what the Purkinje fibers that live within the bundle branches, that's what they're for, to help move that signal faster so that you have your innermost parts of the heart contracting first before the latter half. If you relied on that cell-to-cell conduction to get across, it would A, take too long, and B, wind up with a very disorganized contraction as well. And that's why we don't like things like bundle branch blocks. Last important thing I did want to mention, if you notice where the bundle branch lives, it's just to the inside of the endocardium. And that's what I had discussed a little bit earlier about contractions start at the inside and work their way out through the musculature. Left bundle branch. The left ventricle is so much larger than the right ventricle. And then this one here is actually, we'll go back to this one, is fairly accurate. If you look at how thick the right ventricle is versus the left ventricle, you'll see that this is, let's just go ahead and say that's a 1/4 pounder worth of meat, whereas this one here is a full-blown steak. There is a lot different musculature. And then look at this right atrium. I mean, that's like a thin little strip of bologna by comparison. And that represents how much strength is required to move the blood. You know, this left ventricle is responsible of giving you your blood pressure of 120. That's where that comes from, is the strength of the left ventricle contracting. And because there is so much more mass to the left side of the heart, it requires an additional help to make sure that signal travels in a more even and well-distributed pace, which is why you have the two fascicles, the left posterior and the left anterior. And I know they're difficult to see in this view, but we'll look at those a little closer. What's important is you can actually take these out as separate items. So you could actually have a left bundle branch block, but it's not a complete one. It's incomplete, or also known as a hemiblock, where it doesn't affect conduction necessarily. You won't really see that widened QRS that you would normally look for. Instead, you would just see a certain pattern on the 12 lead, and that's one of the reasons why we use 12 leads, and we'll talk about that later on. Final wrapping up a little bit, let's just talk about the EKG complexes themselves. Actually, I tell you what, we'll stop here and we will come... No, we'll keep going. We will talk about this real quick, though. Your EKG complex. Here she is. You have your isoelectric line. And that isoelectric line is essentially that baseline electrical charge that runs all the way across. It is from there that everything else is measured. Your P wave is the first upright movement from that isoelectric line. P waves are nice and gently rounded, pretty even looking. You then have this nice PR segment through here, and that PR segment represents the AV node holding on to that electrical signal before relaying it, allowing mechanical to catch up with electrical. Total from the start of the P wave to the end of the PR segment is known as your PRI. Very important for a multitude of things. Your PR segment begins when your QRS starts. Your PR segment ends when your QRS starts. Now, that can either be because a Q wave is going down, or it might jump straight into an R wave. Many different versions, but your QRS up and down. And that is this guy here. This point here is what's known as a J point. This section right here from the end of your S wave. When does your S wave end? Your S wave ends when you are back to the isoelectric. Or if your deflection changes, but that's a separate lecture. This point here, though, from the J point to the beginning of the T wave, is your ST segment, and we'll do a lot of stuff with that later. Last but not least is your T wave. Nice, round, bit more of a roller coaster shape to it. It should kind of slope up and then gently trail off. Of course, we find a lot of different P wave related arrhythmias looking at the T wave. Basic EKG paper is going to be as follows. You've got one small box, and that is 1 millimeter on each side. And then you have these larger grids that are a collection of 1, 2, 3, 4, 5 small boxes. Measuring this direction is time, and so that each small box represents 0.04 seconds. Vertically, we're measuring voltage or energy, amplitude. And this one we tend to use just millimeters. So 1 or 2 millimeter elevation, depression, rather than its actual electric value. Measuring left to right, though, that's time. What's really important, though, is that these large boxes, which are, 5 by 5, is that 0.04 times 5, so 0.2 second per large box. Important point keeping. Last but not least, your PRI should be between 0.12 and 0.2. Your QRS should be less than 0.12. And that'll probably be our biggest focuses for today. Your ST segment should be less than 1 millimeter plus or minus. We want that ST segment to be right on the isoelectric line, but even if it's up a millimeter or down a millimeter, not quite as big of a deal. And we'll talk more about that later. Last but not least, R waves. In the event that you have a bundle branch block, you will see that the normal QRS that you're used to, that looks something like that, instead of being a nice, close together, straight upward deflection, because it's been spread out over time, because the left and right bundle branches are not working in unison anymore, instead they're staggered out, you may wind up with two separate peaks. The naming nomenclature is as follows. Large peaks will be given capital R's, a small peak will be given a lowercase r. The second one will be given a prime. So this is what's known as R prime, or lowercase r, capital R prime, because you've got that lovely little mark next to them. These cases can be so extreme that you may actually see it comes back down and your notch here gets below the isoelectric line, and so then you'd actually need to name it an S wave because it has managed to deflect downward below that point, and so you can wind up with an RSR prime. Last thing I'll want to mention is that our first two examples here are a right bundle branch block, but these are classic for a right bundle branch block in lead V1, which is going to be a big portion of our next show. All right, and we'll pick back up here with the layout of the EKG and vectors.